Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimize OR of remaining elements using operations. I was not able to solve this problem during the contest, so this will be an interesting video because I will be sharing you the solution as well as what path I took during the contest and why that path was incorrect. As always, if you stick till the end, you will not only be able to understand the solution of this problem, but take away few things which you can apply in future contests as well. So with that, let's get started. The problem states that you are given a zero indexed array nums and an integer k. In one operation, you can pick any index I and replace nums of I and nums of I plus 1 with nums of I and nums of I plus 1. So you will take two elements and replace it with a single element, which the value of which will be the bitwise AND of the two elements. Now we have to return the minimum possible value of the bitwise OR of the remaining elements of the num after applying at most k operations, right? So let's take an example. Let's say num says 3, 5, 3, 2, 7 and k is 2. That is, we can apply at most 2 operation, and after applying at most 2 operation, our target is to minimize the bitwise OR of the remaining elements of the array. So if you don't apply any operation, what is the bitwise OR? Bitwise OR would be 3 or 5, which would be 7, 7 or 3, which is 7, 7 or 2, which is 7, 7 or 7, which is 7. So currently bitwise OR is 7. Now if you apply one operation with nums of 0 and nums of 1, so what is the operation? Operation is you will replace these two numbers with a single occurrence of nums of I and nums of I plus 1. So if you do 3 and 5, you will be getting 1, right? So after applying this operation, you will be having the array 1, 3, 2, 7. Now what is the bitwise OR now? 1 or 3, which is 3, 3 or 2, which is 3, 3 or 7, which is 7. So currently all the bitwise OR is still 7. Now let's take nums of 2 and nums of 3, which is basically 2 and 7, and again apply the operation. If you again apply the operation, you will be replacing 2 and 7 with the bitwise OR of 2 and 7, bitwise AND of 2 and 7, which will be equals to 2. So the final array would become 1, 3, 2, and the bitwise OR of all the elements here is 3, and you have exhausted all the operations. You have 2 operations, you have done 2 operations, so you can't do more operation. So you are able to reduce the bitwise OR from 7 to 3, and no matter how differently you apply the operations, you will not be able to get to an array where the bitwise OR of every element is less than 3, and hence the answer here is 3. So hope the problem statement is clear. Now how to solve this? As always, because this problem involves bitwise operations, so we will start with a small variation of the problem, which is an easier version. Basically, instead of dealing with numbers, we'll say the number just have one bit, so number can be either 0 or 1. So we have to solve the exact same problem but with a single bit integer, that is the number would be either 0 or 1, right? So what we want to output, the output would be the bitwise OR of all the elements, the minimum bitwise OR of all the elements after applying some k operations, right? So the bitwise OR of all the elements will either be 0 or it will be 1, right? Because the numbers are 0 or 1. Now bitwise OR will be 0 only when everything is 0, right? And bitwise OR will be 1 if any of them is 1. So if we want to, currently the bitwise OR is 1, right? So if we want to reduce the bitwise OR to 0, we have to get away with all the ones from here somehow, and we have to do this within this k operations, right? So I would encourage you to pause and try to think about this smaller version by yourself. So the solution is straightforward. We know that in one operation you can do bitwise AND of two adjacent elements, right? So what you can do is wherever you see 1, you will do a bitwise AND with either the previous or the next element, right? Now if there is at least 1 0 in the entire array, you can take the help of that element and make everything else as 0, right? So let's assume this currently this position 8 is 0. So you can do this operation first. In that way you will remove this 8 and 9 with a single element whose value would be 0, right? In other words, you have removed this one altogether. Now again you will take this, do the operation, 1 and 0 would be 0. So you will remove these two elements with a single occurrence of 0. That is, you also get rid of this one. In the same fashion you will keep on applying this and everything else become 0. So it is evident that if there is at least 1 0 in the given array, we can make the entire array as 0, but we have to somehow figure out the minimum number of operations to make this happen, right? Because we only have k operation. So if minimum number of operation required to make everything as 0 is, let's say, x, we will simply check if k is less than equals to x. If it is true, it means we can use the operations to make everything in the array as 0, and hence the bitwise OR would be 0. If that's not the case, the answer would be 1, right? So hope the approach makes sense. Now the problem is how to figure out the minimum number of operations to make everything here as 0. So the simplest thing is, we have these groups of 1, right? Now if any of them become 0, the rest of them you will be able to make 0 in just one operation, right? So let's say you made 7 0 somehow, right? How you made 0, that doesn't matter, you make 7 0. Now once you have made 7 0, you can simply apply 6 and 7 and remove this 6. You can simply apply 5 and 7, because after removal of 6 these two are adjacent, so you can apply 5 and 7 and this will be removed. After this two removal, this to become adjacent, you will apply this and this will be removed. So basically once you have a 0, you can make every adjacent element as 0 in just one operation, right? So in one operation this will be 0, in one more operation this will be 0, in one more operation it will be 0, right? So wherever you see 1, if there is an adjacent 0, you can make this one as 0 in one operation. So in total, to make everything as 0, you will require 4 operations here. Similarly, to make this one as 0, you will require 1 operation, and similarly to make this one as 0, you require one operation. So in total you require total 6 operations to make everything as 0, which in turn is equals to the count of ones, right? So if the count of 1 is greater than equals to k, the answer would be 1. If the count of 1 is less than equals to k, the answer would be 0, right? Again, all of these is subject to the fact that there is at least 1 0 in the array. If there is no 0 in the array, no matter how many operations you apply, you will not be able to make 0, and hence the answer would always be 1, right? So hope this solution makes sense. What we are doing is essentially, what we have done is here is essentially solve the given problem when the integers are just 1-bit integer, right? So the pseudocode is straightforward. You just need to count the number of ones. You can do it in many ways. One of the ways is you just iterate over the array. If it is 0, you will continue, otherwise you will just keep on counting the number of ones you have and incrementing your result as well, right? Now we have solved the problem for a single bit. Let's move forward with the multi-bit integers, that is the actual 32-bit or 30-bit integer that is given in the problem statement. So when you have this multi-bit integer, so this is just to give you an idea, this 9 is simply 1001, right? Similarly this 6 is 0110, and so on and so forth. Now you have these multiple arrays of ones and zeros, so this denotes 2 power 3, right? This denotes 2 power 2, this denotes 2 power 1, and this denotes 2 power 0. So we already know how to solve when none of these is there and only 2 power 0 is there, right? So all of these problems are identical in itself. Let's say I say that okay, you have to make the second bit as 0 for everything. How many operations are required? It's the exact same problem, right? So what we are trying to do now is we want to minimize the bitwise OR, right? So currently bitwise OR is, let's say, sum O, right? If we want to minimize this O, which bit of O should we first target to unset? Again, to reiterate, we know how to reduce the bitwise OR from 1 to 0 using some algorithm, right? Now we are saying the current array has some bitwise OR of O. We want to make O as minimum as possible. So the obvious choice here is to reduce the largest bit of O to 0. Okay, so in this case the largest bit is 2 power 3, right, which is the third bit in the sequence. So the first goal, or our first goal, should be to reduce this 2 power 3 to 0, right? And if we are able to do this, then O will be reduced, and then we will try and reduce 2 power 2, then we will try and reduce 2 power 1, and then we will try and reduce 2 power 0. So that should be our sequence. Again, why? Because if we reduce 2 power 1, and let's say you require some k dash operation, right, and you reduce 2 power 0, you require some k double dash operation, and after doing these two, you don't have enough operation left to reduce 2 power 3 to 0, and you have actually wasted your k dash and k double dash operations, because if you have utilized those operations in reducing 2 power 3, the overall bitwise OR would be reduced much smaller to a much smaller number, right? So this stems from the fact that 2 power n is actually greater than summation of 2 power I, where I is ranging from 0 to n minus 1, right? So even if you sum everything here, if you reduce 2 power 0, 2 power 1, 2 power 2, even if you reduce all of them to 0, and if you don't like this is one way to reduce all of them to 0, and in the second way you reduce only 2 power 3 to 0 and all of them are 1, the second way is more optimal, or in other words, the bitwise OR in second way would be more smaller, because 2 power 3 in itself is greater than 2 power 2 plus 2 power 1 plus 2 power 0, right? So hope this point makes sense. Basically we'll start from 2 power 3 and try to reduce it to 0, or in other words, try to make every the third bit of every number as 0 by applying some operations, and then we'll try and reduce 2 power 2 and so on and so forth. So the target now is we need to reduce the third bit of every number as 0. So currently this is the third bit of every number, right? And we want everything to be 0 here. So isn't this problem exactly similar to the problem that we just solved before. We want to reduce everything to 0 here, because that's where the bitwise OR would be 0. So how many operations are required? Number of ones. So 1, 2, 3, 4, 5, 6, 7. So there are total 7 operations required to reduce 2 power 3 to 0. Do we have 7 operation? The answer is no. So because the answer is no, no matter what you do, you will not be able to reduce 2 power 3 to 0, right? And because you are not able to make everything as 0, the final bitwise OR would have 1 at least in one of these position, and hence 2 power 3 would be contributed in this row directly or indirectly, right? So now because we know that we can't make 2 power 3 as 0, does it make sense to waste any operation here? The answer is no, because 2 power 3 will be there in the answer. So why to waste operations in making some of these as 0? So we'll only utilize our operations in those numbers where we know we can completely make that 0, right? So we can't do this 2 power 3. So let's just now see 2 power 2. So we are now saying that, okay, can we make 2 power 2 as 0 for everything? So again, let's see this. This is the array. We want everything to be 0. So exactly the same problem. Number of ones is 5, so number of operations will be 5 as well, and k is 6. So basically this means we can make 2 power 2 or the second bit in the bitwise OR as 0, because we can do some sequence of operation that will make the second bit of every number as 0, and because second bit of every number will be 0, in the bitwise OR second bit will also be off, right? So in 5 operations you are able to reduce all the 2 power 2th bit to 0, and you will utilize this 5 operation. Now here is where the problem gets tricky. So now you have utilized 5 operation. So you will say, okay, I have to make everything as 0, so let me apply operations. So you will say, okay, I will make this and this. If I make this and this will be 0 and this will be gone. Now I will make this and this, again this will be 0, this will be gone, again I will make this and this, and so on and so forth. So this works, but now there are other numbers or other bits as well in the number, and because of this the final answer that you will get after applying a sequence of operation can vary from the final array you will get after applying another sequence of operation, right? So if you know that you can make this one as 0, and once you have made this one as 0, you can just propagate it by applying bitwise AND 1 by 1, right? So that is one way. Second way is you make this one as 0, right, and then you propagate it further. So based on which one you choose, the final output will differ, right? So just to give you some visualization, this is how it will be going. Either you will have, so this 4 number will be constant, right? This 4 number will be constant. If you start your operation from here, you propagated this 0 to 1 from here, in other words you will say I will apply bitwise AND for these 2 numbers first. Whatever is the answer, I will apply bitwise AND with this number. Why I'm not checking the bits? Because I only care about second bit, and if I apply bitwise AND, I am sure that this second bit will be 0. So I can apply bitwise AND again, and I am sure that the second bit will again be 0 in the next number as well. So this is one way where you apply bitwise AND of these all numbers to get one number, which is this number, right? So this is one way. Second way is you keep this number as it is. So this number is as it is, you apply bitwise AND of this and this first, and because this is 0 and this is 1, you know that this will become 0 after applying bitwise AND. So you will then keep propagating forward, backward. So these three numbers will remain same, and this number will also remain same, and the value of this number will be equals to the bitwise AND of everything here, right? So you can see the final 5 numbers that we get is actually differ, or actually will differ, depending on what kind of operations you are applying. And that's where I felt back in the problem. I took this path and then started thinking, okay, how can I group operations, or basically you have couple of options. So because you have some options and you want to find the optimal one, I went into recursion and dynamic programming and I lost there. So here is the trick. The trick is, now you don't apply operation right away. You don't know what is the optimal choice of operation, so don't apply operation. Just keep this as it is. Just keep the information that, okay, I can reset 2 power 2 completely in my bitwise OR of the final array. So I can reset 2 power 2, or let's say this is can and this is can't. I can't reset 2 power 3. So keep this information and move forward. So if we move forward, let's say 2 power 2, 2 power 1, you are now trying to reset 2 power 1. So when you are trying to reset 2 power 1, make sure, okay, first of all, 2 power 1 is this array, right? So it has some numbers, right? Now how many operations are required to make 2 power 1 to 0? The answer is number of ones, so 1, 2, 3 and 4 operations. But this 4 operation will be required to only convert 2 power 1 to 0, right? But we have already set that 2 power 2 we can reset, or we will reset, right? So here we'll say, okay, now what I want is, I want 2 power 2 and 2 power 1 both as 0 in every number, and if I can make this happen within k operation, then I will add 2 power 1 to this can list, otherwise I will add 2 power 1 in this can't list, and I will keep on doing this for all the bits, and finally this can't list is the one which will give me my final answer. Okay, so hope you get the intuition. So now the problem statement is, given 2 numbers or 2 bits that you need to reset, how you will be figuring out the minimum number of operations required to make or to reset them, right? So first of all, let's just figure out which all numbers I need to touch. Okay, so see, for 0th number both the bits are already 0, so should I touch 0th number at all? The answer is no, because if both of them are 0, that's what I care. So if they are already 0, I shouldn't touch them, because touching them will require one operation, which is very precious. Like we can't afford spending one operation for nothing or for something else which will come in future. So let's not spend any operation if the numbers are already okay. So we have to spend one operation here, we have to spend some operation here, either one or maybe less than one, right? So we have to spend some operation here, then we have to spend some operation here as well, because at least one of them is 1. We have to spend some operation here, some operation here, here as well, and finally here, right? So in total we have to spend operations in these all places. So we have to spend operation at first index, second index, third, fourth, fifth, and finally 9th index, right? So one, like if you look at it, this is again the exact same 0 1 array, but this time you can say that okay, number of operations required to convert everything to 0 is just number of ones, which is 6, and that will work as well. Like there's no issue with that. In 6 operation you will be able to convert everything to 0. And how? You can simply, you know that there are 2 zeros here, you can simply add these 2 zeros with this, and this will, this 2 become 0, then you will keep on propagating this, and the exact same thing continues. But you can, or there are possibilities where you can convert this entire thing to 0 in less than 6 operations as well now. Why? Because there are 2 bits, right? So if you do bitwise AND of these 2, it may happen that they itself become 0. Why? Because this has 2 bits. It may happen that you have to touch this bit because the first one was set, and you have to touch this bit because the second one was set, right? So if you do bitwise AND among these 2 itself, you will get 0 0, right? So there is no no reason to take the help of an external candidate to make this one as 0 first, and then you take the help of this to make this one as 0. So instead of spending 2 operations, you can combine these 2 among themselves, and in just one operation you can make them 0. So again, this is a possibility, this can happen now. Previously this can't happen because there was just one bit, and if that bit was set, if you do bitwise AND, you will get 1. But now there are 2 bits, and even though it means it has it is 1, basically we have to touch this, but bitwise AND can be 0. And again, when we are saying 0, we don't care about actually 0, we just care about 0 in these 2 bits. Okay, so let's figure out this part. So firstly, no matter what you do, if you AND everything, let's say here, and still you are not able to get 0 0 in both the position, then you can simply take help from one external candidate and you will be able to make 0 0 overall, right? So basically the number of operation will be either 1 2 3 4, and then this one is single one, so there is 1. Either the number of operations will be 5, or the number of operations will be this 4 among themselves are not sufficient, so they have to take the help of another one as well. So this will become 5, and this plus 1 will be 6. So either the answer will be 5 or the answer will be 6. Now we just need to make sure that if they are self-sufficient, I will just subtract 1 and I will get the answer, right? So how to figure out if they are self-sufficient? The answer is just do bitwise AND, right? If you do bitwise AND and figure out that both the bits are 0, then no need to take the help of another one, right? So let's just do bitwise AND of everything here. If you do bitwise AND of these all numbers here, so you will see the first one will still be set, the second one will be 0, but first one will still be set because everything in every of this bit or every of this number, this bit is set. Again, notice that you don't care about other numbers here, you only care about this 2 bit. So when we say it is 0, it means these 2 bits are 0, others may or may not be 0. So in this case, after doing bitwise AND, we saw okay, it is non-zero, so we will take help from one extra outside element, and we'll make it 0. So in total, number of operations required to make everything here as 0 is 5, and number of operations required to make this one as 0 is 1, because this single element you have to apply one operation here, so 1 for this. So total 6 operations are required to convert everything to 0, and we have 6 operations with us. So in 6 operations we can make everything 0. So it means I will simply add 2 power 1 in the can list. So I can convert 2 power 2 and 2 power 1 to 0 in the given number of operations. Now again, what are the operations I am doing doesn't matter, because at the end I just want what all I can reset and what all I can't, right? So till now we have done 2 power 3, 2 power 2, 2 power 1. Now let's try 2 power 0. So the question is, can we reset 2 power 1, 2 power 0 or not, right? So again, if 2 power 0 is unknown, you can simply count the number of ones and that will give you the number of operations required. But 2 power 1, 2 power 0 is not alone now. We have already committed that 2 power 2 and 2 power 1 will be reset for sure. So we have to make sure that along with this 2, if we make 2 power 0 reset as well, is it feasible within the given number of operations or not, right? So again, let's just filter out the numbers which we will touch in some way, right? So this is required to be touched because this is 1 here, so something needs to be changed. Again, this is required to be touched, this will be touched, this will be touched, this will be touched, this will be touched, and finally this will be touched, right? So in total we will touch all these numbers. Now again, we may not, so if you do brute force manner, you will say, okay, count the number of ones, and that many number of operations we will surely be able to convert everything to 0. So in 1 2 3 4 5 6 7 operations, it is sure that I will be able to convert everything to 0. But because there are more than 1 bits involved, you may not need to take the help of external candidate to make the first 0, and hence you can try, or you can have less than 7 operations as well, in which you will be able to make everything as 0, right? So what's the process for that? So let's start with the first 2 bitwise AND. So if you do bitwise AND of 6 and 9, the answer would be 0, right? There is nothing common between 6. Okay, let's just get rid of these, right? So if you do bitwise AND of 6 and 9, the answer would be 0 because there is nothing common. So because the answer is 0 here, you will stop here directly, right? You will not take this 0 and bitwise AND with 12. Again, this you can do, but this 12 along with this 6 or some other element in the right may be self-sufficient to make another 0. Hence, if just as soon as you make 0, you just stop here and don't apply this operation until absolutely needed. So what you will do, you found 1 0, you will say, okay, in one operation I have made this thing as 0, that's fine, good. Now let's start with 12. So again, in one operation 12 and 6, if you do 12 and 6, it will be getting 4, right? So if you do 12 and 6, the only bit common is this 4th one, so you will get 4. Now 4 is not 0. Again, notice 0 here means these 3 ones should be 0, right? The second bit, third bit, sorry, first 0th bit, first bit and second bit should be 0. Here the second bit is not 0, so it is actually not 0. Now 4, we will do bitwise AND of this with 13, so 4 and 13. So if you do, this is 13, right? So 13 and 4 will again be 4, right? So it will be again 4, right? Again not 0, so 4 and 14, so 14 is something like this. If you do 4 and 14, again it will be coming as 4, so again not 0. So you have applied some operation for all the ones that you want to change, and you said you ended up having 4. In other words, you doesn't have, or they are not able to satisfy among themselves. So then you will just take the help of one adjacent element, either this 0, either you make this connection or you make this connection, whatever you want. You just make one connection, or you just have to make one extra connection to make this as 0. So you have done 3 operations. Now you have to do one more operation, so in total 4 operations. You are now able to convert these 4 as 0 as well. Now finally this is the one remaining, and for this because it is alone, there is no way you can make it self-sufficient, so you have to take the help of external one. So you will require one more operation to make it 0. So in total you require 6 operations to make everything as 0. And remember, if you have done this brute force manner, you would have required 7 operations, right? Because you have taken the advantage of the fact that you have more than 1 bits, and if you combine them among themselves, they may be self-sufficient to cater to the requirement of the required bits to be 0. So hence we are able to convert 2 power 2, 2 power 1 and 2 power 0, all of them to 0 in just 6 operations, and hence we will simply add 2 power 0 in this list. Had we not be able to convert this 2 power 0 to 0, we will simply remove this from here and add it here, and we'll move forward, right? So in this particular case we are able to, so we'll add it here. So in total can't just have 2 power 3, so we'll say the answer is 8. Basically the bitwise OR of everything at the end will be 8. Why? Because this is the only bit that we were not able to reset within the 6 operations. Others we are able to reset within 6 operations itself, right? So hope this entire solutions make sense. If you have any doubts, I would strongly encourage you to rewind and watch the section which watch this last section a few times to grasp what has been discussed here. In essence, the main crux of the solution lies in the fact that you don't start applying the operation in the first iteration itself. So notice the first iteration we noticed was 2 power 2, right? And we noticed that okay, there are like we just need 5 operations here. So we'll not apply this 5 operation directly here, because applying 5 operation would have certain semantics. Basically you may or may not have the most optimal array at the end. So to avoid going in that direction, what we have done is instead said that okay, 2 power 2 is, I know that I can convert everything, every bit, other bit, 2 power 2th bit of every number as 0. So that's fine. I will now try the next possible bit, and for that bit I will see if I can reset it along with the previous one, right? Because the previous one is something I have promised that I will be resetting. So along with the previous one, if I can reset that, and to that, for doing that, you just do the exact same operation but with a slightly different format, because now you just don't need to count number of ones. You may have less than that number of ones operations as well. Why? Because there are various bits. So if you do bitwise and of 2 numbers among ones itself, you may not be getting all the ones here. You may be getting 0 and they may be self-sufficient to cater. Again, let's just close this part. Let's say this is 17, right, and this is 6, or let's say this is 14, right, and sorry 6, yeah, let's say it is 14 and this is not 17. Okay, so 16 plus 6 22 and 16 plus 9 25, right? So let's say this is 25, this is 22. If you do bitwise AND, this will give you 8, right? And 8 is not 0, but we will consider 8 as 0 because we only care about 4 and 2. So neither 2 power 2, neither 2 power, not 2 power 1 bit is set. So for us, even though the actual value is not 0, we'll consider this as 0, right? So we only care about 2 power 2 and 2 power 1, and how to, well, just check whether these two bits are 0 in this or not. If they are, our job is done, right? So hope this solution makes sense. Let's quickly look at the pseudo code. So if you remember, this was the previous pseudo code where we're just counting the number of ones. So basically what we are trying to write the pseudo code for is, if you have a array of ones and zeros, right, and you want to understand how many operations or minimum number of operations required to make everything as 0, then what will be the value? So if it was the first bit itself, this is the algorithm, or in other words, if it is a single bit number, this is the algorithm. But if it is a multi-bit number, 1 and 1 is not actually 1 because it's actually something else, right? So that's where what we have done is the exact same thing. The only difference here is we also have this AND value with us. So we keep on calculating AND value until the target, until we got 0. So target is basically all the bits that we are trying to set. So if there is any overlap, then basically there is at least one of those bits which is not yet set. So we will set, so we will continue. If every bit in the target is 0 in the AND so far, then this value will evaluate to 0 and we will stop. Basically we got one self-sufficient set of numbers that are able to make 0, right? So we will keep on doing AND until we hit, until we exhaust all the ones, right, all the consecutive ones, or we hit a number where up till which the bits we care about is all 0, right? Now one of these conditions is satisfied, and if the first condition is satisfied, total number of operations required would be the number of elements we have visited minus 1, right? And if the second condition is satisfied, the number of operations would be required equals to total numbers we have visited. Basically, if you have visited 5 numbers, you will be having 4 operations, and after 4 operations you are not able to make 0, so you just take the help of another one to make it 0. So number of ones is equals to the number of operations here. In other case, you just subtract minus 1 because you don't need to take the help of any external zeros to make 0, right? So we'll keep on doing this, and notice that we may not traverse all the consecutive ones here, right? We have seen one example in the previous iteration where we stop here. We haven't traversed all the consecutive ones as well, so we'll just stop as soon as we get 0 so that we can save operation, right? So just this part is something you need to keep in mind while implementing. Rest are exactly straightforward. So this algorithm will give you the minimum number of operations required to make every bit that you have in target as 0, and if this minimum number of operations is less than or equals to k, the latest bit that you are trying to capture, you will keep it in the can list, otherwise you will keep it in the can't list. And after iterating over all the bits, you will just go through your can't list, and whatever bit is not we can't reset, we'll just add it to, we'll just reflect that in the answer, right? So if you have watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself. So next we'll be looking at the code. Again, if you haven't tried it yet, just pause and try by yourself, otherwise you will not be able to understand what's there in the problem, and you'll not be able to approach this kind of problems in future by yourself. So the code is exactly what we have discussed. So this is the minimum number of operations. This algorithm is exactly the pseudo code that we have discussed here. We'll come to that. Let's say you have minimum number of operations that you can there is a function minimum number of operations which will give you the minimum operations required to convert everything that is set in target to 0, right? So if you want to convert 2 power 2 and 2 power 1, these two bits are 0, you will set target as 5, right, which is 2 power 2 and 2 power 1 bit set. Sorry, target at 6, which is 2 power 2 and 2 power 1 bit set. If you want to check for these 3 bits, you will set these 3 bits, which is target will be 7, right? So that's what target denotes. So as discussed, we will start from the last bit and go all the way to the first bit, because the weightage of last bit is the maximum, right? So we checked the last bit. This is what we want actually. So this reverse answer basically is the number of all of the things in the can list. So can list has something, we want to add this to the can list as well and check if it is possible or not, right? So this is what we are checking, whether it is possible or not. So we just figured out this boolean array, which basically says do we need to touch this or not, right? So basically if these are 3 bits we are considering, is any of these 3 bits is set at 0th index or not. That's what this taken array would denote. Now once you have this taken array, you will just call this minimum operations with your target, and it will give you the number of operations required, and if it is less than equals to k, it means you will add it to your can list. So you will just make your can list as this one, otherwise you will add it to your can't list, and can't list in our case is answer, so we just add it to our can't list. Now finally, what is the minimum operation function? Minimum operation function takes in 3 things: target, which is all the bits that we want to be unset at the end in all the numbers itself, and what all numbers we want to touch, like basically any of these bits, all the numbers where any of these bits is at least set, one of these bits is at least set here, right? So we'll just iterate over all the indexes from 0 to n. If it is not set, or if we don't want to modify it, so no worries, we'll not modify it at all, we'll move forward. If it is something that we have to modify, then we will start from the current index, keep on doing and bitwise and with the next possible indexes. So just to reiterate this part the one last time, if these are the values, so we will keep on doing and with the next numbers that you have, because this, if this is 1, it means it requires some operation or some modification is required for sure. So you will, instead of doing it with something which doesn't require any modification, you first try with the one that requires modification, and if you are able to do all zeros among themselves, that's the best thing you can have, right? So we'll keep on doing and until we get 0. As soon as we get 0, or we have exhausted all the consecutive ones, either one of these cases true. So if the first case is true, that is we get all zeros, then we'll stop there and start a new group from the next index. So in the previous case, if you remember, let's just get rid of all of these. So if you remember, we had a 0 here, so if we start from here, we will have a 0 here, 9 and 6 will be 0. So if we have a 0 here, or the again 0 here means with the bits which we care about, these are all the bits which we care about. So if you do bitwise AND, it will give you whether any of these bits is set or not. So it will only give non-zero value if one of these bits is set, otherwise it will give you some zero itself if all of these bits are not set. So if any of these bits is set, this will be evaluated non-zero. So if all of the bits are unset, then we know that we got one group which among itself is able to make 0. So number of operations required would be 1 less, right? Otherwise number of operations will be required would be the number of ones we have visited, which is j minus st, right? So we'll keep on doing this for all the numbers, and finally the answer will contain the number of operations required to make everything as 0, or every bit in the target as 0. So hope this entire solution makes sense. If you have any doubts in any of the piece, feel free to follow up in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.